What is a significance test? A significance test is a formal method to test a claim. You may have learned about confidence intervals before this, which are used to estimate a population parameter when it is not known. That's generally how I start teaching. The best way to learn about a significance test is to just jump right into a problem, because you can kind of intuitively get some of this, and I'll try and teach some of the formal parts along with the intuitive. Now, I've made this problem up. DeAndre Jordan has never made this claim, but let's suppose, for the sake of the problem, he does. DeAndre Jordan of the Los Angeles Clippers claims that he is a 60% free throw shooter. As a manager, or as his manager, you decide to see if there's any truth to his claim. You have him go to the line and shoot 50 free throws. He makes 23 of them. So you might ask yourself immediately, well, is his claim true? I mean, is 23 out of line when you're a 60% free throw shooter? In statistics, with a significance test, we can model this to see. And that's where you'd start. So we're going to introduce, I'll introduce here the first topic, and that's the null hypothesis. So you might ask yourself, well, let's just assume he's not exaggerating. He should make 30 out of 50 most of the time. Okay, this is the null hypothesis. We're going to assume that he is correct, and he is going to make 30 out of 50. And we're going to set up a simulation to simulate this, just to see what happens when you do this. This null hypothesis is always represented with an H and a subscripted 0, which stands for 0 standing for initial hypothesis, null hypothesis. And this is the symbolic representation for it, this H sub O equals 0.6. Usually right now we would talk about an alternative hypothesis, but let's just absorb what we have. So the first thing we're going to talk about is I'm going to show this simulation using a program called Tinkerplots. And I've got it mostly set up for us here, so we can just kind of look at it quickly, just to kind of show you what some of the things are. Most importantly here is this is my simulator. So this is set up where it's a spinner, where 60% of the time that you spin this, it'll land on make, and 40% it'll land on miss. So I'm going to slow it down just to show you this thing working. So there's his first shot, it was a make. There's his second shot, it was a make. Third shot, make. Fourth shot coming up, miss. And he's going to do this 50 times. So this is representing him shooting those 50 shots. So let's speed that thing up. And now I've already done it twice. So it's collecting over here. Here's each sample. This time he made 32 total and he missed 18 out of 50. And I'm going to go ahead and collect the makes in this table here. So we've done it twice. Let's do it one more time, 3 times, 4 times. So each time this is out of 50. So he shot 50 free throws, he made 28 the 4th time. You know, you'd wear the poor guy out if you did this in real life. So here we go. We're going to go ahead and do this 100 times. So there's 6, there's 7, 50, 51, 52, 96, 97, 98, 99, 100. Whew. So we've got 100 sets of 50 shots in each set, and this is our makes. So now I'm going to pull a plot in here to plot all of those, that entire table. There it is. I'll kind of make it take up the whole screen, or as much of it as I can. Kind of get things out of my way. And here's all 100 of those makes. So I'll pull this thing around. Maybe adjust it a little bit. 41, maybe let's go 45. Let's make my bin width 1 so we can see each shot. Yeah, that looks pretty good. And then we'll stack them so we can kind of look at this. And as you can see here, we have a fairly normal looking curve with a, looks like the mean here is about 30, or median. Looks like our mode occurred at 31. But you can kind of just see this nice shape forming. And if we did it, you could imagine doing this 400 or 500, 600 times, that you'd get this really nice distribution if you just kept going. But let's look at our null hypothesis. Was we assumed that this is true, that he didn't shoot 60%, and we're going to introduce the next thing, which is a p-value. So once we have a simulation done of what we assume is true, based on our simulation, we might ask ourselves, how likely is it for a 60% shooter to make 23 or less free throws out of 50? We call this a p-value. And in our case, with our simulation, we can see that 23 or less, we had 2 of those. So our p-value is 2 out of 100. I'll try and put that in here, or 0.02. So 2 out of our 100 simulations. So our p-value is 0.02. So we can then kind of see that this is kind of a rare event. You know, how rare? That gets into a thing called alpha level, and we'll talk about that later. But generally, we want to look at it this way. An outcome that would rarely happen if the hypothesis is true is pretty good evidence that it may not be true. So we've got some evidence here suggesting that he indeed is not a 60% shooter. And that's the alternative hypothesis, symbolically represented as HA. And so in this case, you know, like I said before, there is evidence to suggest that Jordan was exaggerating and his free throw percentage is less than 60%. And we'd symbolically represent the alternative hypothesis, HA. In our case, this is a one-sided test because we're only going to test if it's less than 0.6. So HA is less than, H sub A is less than 0.6. So let's take a few minutes and talk about statistical significance and the alpha level. So level alpha. When should we reject or fail to reject the null hypothesis? So in our case, the null hypothesis, if you remember, was 0.6. And generally, they set an alpha, you know, statisticians just generally set an alpha level at 0.05. So at anything below 0.05, we would consider that to be a rare event. It doesn't happen by chance very often. But there's no hard and fast rule for setting alpha levels. Generally, you look at 2 situations. If it's plausible, like look at plausibility. If it is a strongly held belief, if that null hypothesis is a really strongly held belief, we may need a small alpha level to convince somebody of its of its implausibility. And you all should look at the consequences. So if we reject the null hypothesis, will that be expensive? You know, those are 2 things that might help us determine an alpha level. Because you might use an alpha level anything less than 10%, anything less than 0.1. So let's put all of this together. So if you put all of this together, we had a null hypothesis P of 0.6. we had an alternate hypothesis, meant to write an H there. We had an alternate hypothesis of P being less than 0.6. We ran a simulation. If you look back at our simulation, and we found that two of these, this one and this one, we found two of these out of the 100 occurred less than 23 times. And so we had a p-value of 2%. Or 0.02. So this tells us if we chose an alpha level of 0.05, and you usually set that alpha level before you run your simulations or before you run the test itself. So you don't just set an alpha level based on the p-value. But in our case, the p-value is less than the alpha level, so we would consider this a rare event, and we would reject the null hypothesis. We would reject that his free throw percentage is 60%, and conclude that there is reason to believe that he could have a free throw percentage that is less than 60%. So we would never say 100% that he is definitely does not have a free throw percentage of 60%. We would just say the evidence suggests that his free throw percentage is less than 60%. So that's a significance test from beginning to end. It's not formal by any means, but hopefully that introduces you to all the terminology in play, and hopefully it makes a little bit of sense to you. Hope it helps. See you next time.